In this video, we're going to learn about infinite series and how they differ from infinite sequences. So in general, the difference between a sequence and a series, we talked about a sequence in this last section, and it's just a list of numbers separated by commas, and it can be any list of numbers. And in the last section, we focused a lot on finding the limit of this list of numbers based on some pattern. And so now for a series is the sum. So this is the symbol, it's the Greek letter sigma, and it means the sum of a sub n, which we said was just a list of numbers. We can also write this list of numbers as a specific formula. And so this is a list of numbers that has been added or subtracted. So it is no longer a list separated by commas. Now we are separated by a plus or minus sign, so consecutive terms are added or subtracted. And so starting off with just an example of a sequence, we want to list the first 5 terms of a sub n is equal to 2n minus 1. If I want to list the first 5 terms, I can find, let's say this starts at n equals 1. If we're not told otherwise, we can start this at 1, and so a sub 1 is equal to what happens when I plug 1 into this expression. So that's going to be 2 times 1 minus 1, which is 1. A sub 2, when I plug a 2 in for n, I get 4 minus 1, which is 3. A3, when I plug a 3 in, I get 6 minus 1, which is 5. A4, when I plug in a 4, I get 8 minus 1, which is 7. And A5, when I plug in a 5, I get 10 minus 1, which is 9. Essentially just a list of odd numbers. And if I wanted to list the first 5 terms, I could list them 1, 3, 5, 7, and 9, assuming that we're starting at n equals 1. And now let's see how this differs from the first 5 partial sums. And now these are called partial sums because we are adding together some of these values. And so let's look at this. Now I'm going to denote this first partial sum s sub 1, just s, to show that this is the sum. And that's just going to be, well, the sum of the first value. That's just going to be 1. And now s sub 2. This is going to be this first value plus this second value. We're finding the sum of the first 2 terms. And so this is going to be a1 plus a2, which is going to be 1 plus 3, and we know that that's 4. So this is S2. Let me just make it clear that S1 is just A1, which is 1. All right, and now for S3. In the same way, this is going to be A1 plus A2 plus A3, which is 1 plus 3 plus 5, and I know this is 9. Then we have S4, which is A1 plus A2 plus A3 plus A4, just following this pattern. And so that's going to be 1 plus 3 plus 5 plus 7. And I'm really just taking 9 and adding 7, and that's going to be 16. And finally, S5, you might have noticed the pattern by now. I'm just adding A1 through A5. And this is going to be 1 plus 3 plus 5 plus 7 plus 9. I know 16 plus 9 is 25. And so now when I'm listing the first 5 partial sums, it's going to be these values here: 1, 4, 9, 16, and 25. And so we have a basic example of this difference between the first 5 terms of a sequence and the first 5 partial sums of a series. All right, now let's look at another idea, another way to represent a series. And that's with an infinite decimal. And so what if we have the constant pi? Well, the convention behind this decimal notation in general is that any number can be written as an infinite sum. Here, where we have these three dots, this just indicates that the sum continues forever, therefore being an infinite sum. In this decimal approximation of pi, I know that the more digits I include, the closer I'm actually getting to finding pi. Because this is an irrational number, this decimal won't repeat itself and it won't end. And so the more digits I include to the right of this decimal, the more accurate this estimation is. And the same thing applies when we write this as an infinite sum. The more terms we include, the closer we get to the actual value of pi. And all of this with the denominator of 10 and then 100 and then 1,000, this is where we get that tens place, hundredths place, thousandths place, 10,000ths place, and so on. So this idea is just where we got the notation for our decimal number system. We're just now thinking of this in terms of a sequence. So if we try to add the terms of an infinite sequence, we get an expression in the form of a1 plus a2 plus a3, adding all of these terms together, which is called an infinite series. And it's denoted in these two ways. Let me write these out. This is the sum starting at n equals 1 and going to infinity of a sub n, or we just have the summation of a sub n. This just denotes that it is what happens when we add together the terms of an infinite sequence. So we're adding together all of these terms of an infinite sequence. And again, when we don't have any kind of bounds on top and below this summation symbol, it is assumed that we're starting at 1 and going to infinity. So if we see this, we're assuming that we're starting at n equals 1 and that this is an infinite series. And so let's look at this first example of a series. So here we can see the relationship between consecutive values, and that's just that we're adding 1 to each consecutive value. Now if I were to try to find the finite sum, finite just means not infinite, it ends, for this series, I can't find one. Because if I start adding these terms together, S1 is just going to be A1, so that's going to be 1. S2 is going to be what happens when I add these first two terms together, so that's going to be 3. S3 is going to be what happens when I add these first three terms together. And so this is just the sum written as a list. So this is just the series written as a list. This means that after the nth term, so as I continue on, this sum, I'm looking to find the pattern to describe this set of values, and that's going to be n times n plus 1 over 2. Now I can see that as n increases, this list is just going to continue to increase. So this n times n plus 1 over 2 becomes very large as n increases. And so I can say that the sum of all of these values is going to be infinite. It's not going to end. Now let's look at this other series. In this other series, I have 1/2 plus 1/4 plus 1/8 plus 1/16. I can see what's happening to the denominator as I'm just multiplying this denominator by 2. And so this means that if I start adding the terms together in the series, S1 is going to be just 1/2. S2 is going to be 1/2 plus 1/4, which is 3/4. S3, 1/2 plus 1/4 plus 1/8, and we can see that same pattern happening here. And if I find a general rule for all of these terms, if I want a formula for all of these terms, I get 1 minus 1 over 2n. Now let's look at what happens as my n increases. And so each value in this series is getting smaller and smaller. This means that I can see that the difference between consecutive terms in our series is smaller and smaller. And if I look at the fractions alone, I can see that I'm starting with 1/2, then I go to 31 over 32, and then 63 over 64, and so I'm getting closer and closer to 1. And if I find that table in the calculator, that's exactly what I can see, is that the sum of my first n terms, well, at n equals 1, it looks like 0.5. But then as our n gets larger and larger, this gets very, very close to 1. So this value is very close to 1. And I can easily find a table like this in the calculator, and so let's do that. And so starting off by going to y equals, making sure I'm back in function mode. And now instead of just typing in 1 over 2 to the power of n, I want this to be a series, not a sequence. And so I'm actually going to go to math, and then if I keep scrolling down, I can find the summation. So this is summation, item 0. If you have one of the newer calculators, you're going to get something that looks like what we see this notation being. If you have an older calculator, I think this is only valid for the TI-83, there are instructions for your inputs on this worksheet. And so for our purposes, I'm going to start the variable off at 1. Now my variable is going to show up as an x. I know that we denote this n typically, but it doesn't affect anything. And so I'm going to start this off at x equals 1. Now this is an infinite series, and so my maximum, rather than typing in infinity, is just going to be whatever I want to make it, again, assigning that a variable. And now I'm going to type inside of my summation that 1 divided by 2 to the power of my variable. And if I go to the table, I can see the sum of my first n terms. I know this is only valid starting at 1, and so this is actually going to give me not just that item, but the summation with this certain n value. And so I can see that as my n, which is listed as my x, increases, I can see that I'm getting closer and closer to 1. And sometimes your calculator will only display 3 or 4 digits, but with our cursor on it, we can see that we are getting closer and closer to 1. We're not actually reaching 1. Don't think that just because we see a 1 here, that means this is actually a 1. It's just all our calculator can display. This is just the calculator rounding. And so we're getting closer and closer to 1. And so what this means is that the sum of this infinite series is 1. The sum of this infinite series is 1. And so let's summarize what we did here. So we created a new sequence of the partial sums. So this was a sequence of the partial sums. We created a sequence of the partial sums, and then we found what happened as n got larger and larger. Well, can't we also say that we found out what happened to this sequence of partial sums as n approached infinity? And what does this sound like? This sounds a whole lot like a limit. And so we can conclude that the sum of a series is the limit of the sequence of partial sums. So we're creating a sequence of partial sums and finding the limit of that sequence of partial sums. And if the limit exists, then we can call this number s the sum of the series. So if we find the limit and this gives us a constant, then this converges. If we find that the sum is equal to infinity, in other words, if we find that the limit does not exist or goes to infinity, then we can conclude that the series is divergent. So we saw something similar as far as integrals went. Remember when we did the improper integral? when I wanted to find an improper integral, when my bounds went from 1 to infinity, kind of like our bounds here, my n is going from 1 to infinity, I can't exactly evaluate this expression at infinity, much like I can't evaluate the antiderivative of f of x at infinity, but I can figure out what happens as this upper bound approaches infinity by the use of this other variable t. In this case, I can find out what happens as n approaches infinity. And so let's do a couple of examples. And in these next examples, we're really going to nail down the difference between a sequence and a series. And so let's start off by finding the limit of each sequence. Now I know these are sequences because it's just a list of values that are separated by commas. So I just want to know that if there's a pattern, if all of these values are approaching some constant. And so on the left here, to find the limit of this sequence, well, all I'm doing is finding the limit as n approaches infinity of this sequence. And the rule of this sequence is just n. I can see that each of these values, a sub 1, is just that value of n, which is 1. A sub 2 is just that value of n, which is 2. So I'm just finding the limit as n approaches infinity of n. And all I have to do is I need to plug infinity into n, and I get, well, infinity. So I found that the limit of this first sequence is just infinity. So this sequence does not converge. And I can write that this sequence diverges. On the right here, now the rule for this sequence is 1 over 2 to the power of n. And so let's find the limit as n approaches infinity of 1 over 2 to the power of n. Well, now when I plug in this infinity for n, I get 1 over 2 to the power of infinity. 2 to the power of infinity. Well, 2 to the power of infinity is just going to approach infinity. And when this approaches 1 over infinity, as my denominator gets larger and larger, this fraction is going to approach 0. And I can say that this this sequence does converge. And now let's find the limit of these series. So these are no longer sequences, this is just a series. And I'm remembering that to find the limit of a series, I am looking at the limit of the sequence of partial sums. And I have a formula for the sequence of partial sums, and that is n times n plus 1 over 2. So this is what I'm finding the limit of. The limit as n approaches infinity of n times n plus 1 over 2. Well, I can simplify this numerator. I can call this n squared plus n over 2. When I plug infinity into this expression, my numerator is going to go to infinity. My denominator is going to stay at 2, which is going to give me a limit of infinity. Therefore, this series has an infinite sum. The sum, I can really say it has no sum. It doesn't have a finite sum. Now let's look at this next example. Here I see that this sequence has just been made into a series. And so this is the series of 1 over 2 to the power of n as opposed to the sequence of 1 over 2 to the power of n. In this series, I'm adding together all of these values, and in the sequence version of this, all of these values are just separated by commas. And I can represent this series as a sequence of the partial sums. So I can represent a series as a sequence of partial sums. And let's just make a note that that's what we see here. This is the sequence of partial sums. And I found the actual rule for this sequence of partial sums, and this is what I'm going to find the limit of. And so the limit as n approaches infinity of 1 minus 1 over 2 to the power of n is going to approach what happens when I plug in infinity. That's going to be 1 minus 1 over, and this denominator is going to go to infinity. I know when my denominator gets infinitely larger, this term is just going to go to 0. And so my limit is going to be equal to 1. And so this converges. We see the difference between the limit of this sequence and the limit of this series. The limit of this sequence is 0. That says that as n increases, these terms are going to get smaller and smaller, but the limit of this series is 1, meaning the sum of this series is equal to 1. So the sum of this series is equal to 1. Which is what we found earlier using our calculators. Okay, let's do another example. Example 3. If S sub n is equal to a1 plus a2 all the way to an, which is equal to 2n over 3n plus 5, find the sum of the series. We're given this note here that this formula is for the sum. So this formula is for the sum. So I'm actually not even given the individual components because quite frankly it doesn't matter what they are. All I'm looking for is the sum of the series. So the sequence that this comes from actually doesn't matter. It can only really be used to find the formula for this series. And so now I'm finding the limit as n approaches infinity of 2n over 3n plus 5. And I could plug in infinity, and I could use L'Hopital's rule because this would give me infinity over infinity. Using L'Hopital's rule, taking the derivative of the numerator, I'm left with 2. Derivative of the denominator is 3. And so the limit is equal to 2/3. Or I could do the shortcut way, and I could say because the degree of the numerator is equal to the degree of the denominator, my limit is just the fraction of leading coefficients. And so my limit is just 2/3. So however you want to find this limit, I found that because I have a finite limit, the sum of the series is equal to 2/3. And that is all there is to it. These problems are really short. They require more thinking than work. So that's kind of nice. Example 4, we want to calculate the sum of the series. And again, we're just given that rule for the sum because that's all we need. And so to calculate the sum, I want to find the limit as n approaches infinity of this series n squared minus 2 over 3n squared plus 5. And because n is approaching infinity and the degree of the numerator is equal to the degree of the denominator, in front of this n squared, I really have a coefficient of 1, then I can say the limit is just equal to 1/3, meaning that the sum of the series is 1/3. And so now let's talk about some specific types of series. And so in the last section, we talked about a geometric sequence. Now we're going to talk about a geometric series. So a geometric series is essentially the series version of a geometric sequence in which we have a common ratio between terms. So each term is obtained from the preceding one by multiplying it by the common ratio r. Now, instead of it being a list of all of these values, we're adding these together. And again, to get from A to AR, we're just multiplying by R. To get from AR to AR squared, we're just multiplying by R, and so on. So we're multiplying by this common ratio, and make this clear, this is multiplication. We're multiplying by this common ratio, R. And so assuming this this leading coefficient isn't a 0, because then all the terms would just be multiplied by 0, we have our summation form of this geometric series, where we have A, some coefficient, times R to the power of n minus 1. And the reason this power is n minus 1 and not n is because if our first n is 1, we know that R to the power of 0 is 1, and so this is going to give us that first term of A. That's the reason for this exponent being subtracted by 1. And now let's figure out how we can find the formula for the sum of a geometric series. Now, if r is equal to 1, if the common ratio between terms is equal to 1, what that means is that my first term is just whatever this a value is, so it's just this coefficient. My second term is just a times 1, okay, which is just a. And if I ever have any value, it doesn't matter how large or how small a is. If a is 1/10,000th, and I'm adding to it an infinite number of these 1/10,000ths, I'm still not going to converge. This geometric series will still diverge to either positive or negative infinity. If I have a huge a, well, this is going to get very, very large very quickly. Still positive or negative infinity. But now what if r is not equal to 1? It gets a lot more interesting. Now I have this notation that just shows that I'm talking about a geometric series. That's why I have this s sub n. And we said that we're just adding together all of these terms. Now I'm going to do a little bit of algebra to get a simplified definition of this sum. And so what I'm doing here is I'm just multiplying both sides by r. So I'm multiplying the left side by r, okay, and I'm multiplying everything on the right side by r. And that's how we got this expression down here. On the left of the equal sign, we just have r s sub n, and on the right side, you can see that each of these terms was just multiplied by r. A became AR became AR squared, and the last term, AR to the power of n minus 1, just became AR to the power of n. And now that we've got these two equations that are equivalent, all we're doing is subtracting them. If we subtract these equations, well, then I'm left with s sub n minus r s sub n on the left. And then on the right, all of these terms are going to cancel, except for the first term in this first version of the equation. All of these other terms are going to cancel. And the last term in the second version of the equation, we just have a minus ar to the power of n, okay? Then if I want to isolate this s sub n, then I can just factor it out on the left-hand side. If I factor out an s sub n on the left-hand side, I'm left with 1 minus r. To isolate this s sub n, divide both sides by 1 minus r. And that's how I get to this equation. It's divided both sides by 1 minus r. So essentially what we did was we turned an infinite series, just using valid algebraic techniques, into a summarized form where I can now look at a limit. And so if I go back to the sequence version of this, I know that if I'm looking at all of the items in this geometric sequence, remember, that we said a geometric sequence converges in the form r to some n converges when the absolute value of r is less than 1. And so if this is true, if this is our situation, then we can look at the convergence or divergence of this geometric series. Now, why is this important? Because if I'm thinking of the sequence, I'm just thinking of all of these individual values. If a list of these values does not converge to some constant, there's no way that when I add these values together, it's going to converge. That's why I just kind of want to ensure that this sequence is convergent first, because if the sequence diverges, then when I add up all of these values, that's also going to diverge. And so let's look at the limit of this series now when n approaches infinity. And when n approaches infinity, I am left with this r to the power of n. We said that we're dealing with the situation where r is between -1 and 1, not inclusive. So this term is going to go to 0. So we'll just be left with a times 1 in the numerator, and the denominator is just going to be a times 1 minus r. And so because of this, when the absolute value of r is less than 1, the geometric series is convergent, and its sum is a over 1 minus r. We know that a just stands for the first term, and r just stands for the common ratio, and this is the sum of the geometric series when r is between -1 and 1. Now, this inclusive-exclusive thing is important. Inclusive means I'm including that value. So if r is less than or equal to, and this should be a -1, that's fixed on your notes. You should see a -1 right here. Or r is greater than 1. The sequence is divergent, because remember, this alternating geometric sequence, is divergent. So -1 to the power of n diverges, because it's alternating between -1 and +1. And so if this is not true, then the sequence is divergent and the limit does not exist. Therefore, geometric series diverges in those cases. So r must be between -1 and +1, or the absolute value of r must be less than 1 for the geometric series to converge and converge to this sum. And we just have a little summary of everything we just kind of proved above. And naturally, if r is outside of this range of -1 to +1, if I have something like 3/2 raised to the power of n, as n gets larger and larger, this fraction is going to get larger and larger. So that's kind of a rationale for this r value being between -1 and +1. And with that, let's find the sum of this geometric series. And to find the sum, we first need to find out, well, if this converges in general. And so let's find this value of r. We want to find the common ratio r. And because we're told that this is a geometric series, we can assume that the common ratio is the number that we multiply each term by to get the next term. So we don't really have to prove this is geometric because it's stated in the problem. And so let me just use the first two terms. What I'm saying is I'm multiplying 5 by something, the common ratio, to get my next term, which is -10/3. Again, I can use any two terms. I have the same equation. This r should be the same as -10/3 times r is equal to 20/9. but I'm just going to use the first terms. Just solving for r, dividing both sides by 5, I get that r is equal to -10/15. And simplifying that fraction, I get that r is equal to -2/3. Because this is a geometric series, I'm looking at my r value to see if it converges or diverges. And my question is the absolute value of r less than 1? Well, the absolute value of -2/3 is 2/3, which is less than 1. Great. And so the series converges. All right. And now that this converges, and we could argue that if we're told to find the sum, it probably converges. Now let's find the sum, and because the absolute value of r is less than 1, we can use this formula for the sum. And so our sum is going to be equal to a over 1 minus r, and a is just the first term. And so our first term is just a, which is 5. And so now I can find the sum, and the sum of this geometric series is 5 over 1 minus r, so 1 minus -2/3. And let's simplify this. This is going to be 5 over 1 plus 2/3, which is 5/3. This is going to give me 5 times 3/5, which is 15/5. And so my sum is just going to simplify to 3. So my sum of this geometric series is 3. All right. Now be very careful with this. If I find the sum to be a constant, but my r is greater than 1, then it's going to give me the false impression that this is convergent. This is only true if I've already found that the absolute value of r is less than 1. Only if this is true. Now what does this really mean, that the sum of the series is 3? And what this means is that essentially, while we can't literally add an infinite number of terms one by one, the total sum is the limit of the sequence of partial sums. So if I were to create that list of partial sums, so if I were to create a sequence, which is just our term for a list of all of these partial sums. So the first partial sum would be 5. The second would be 5 plus a -10/3. The third would be 5 plus a -10/3 plus 29. So what we did before, then I'm finding the limit of that sequence. And if I look at this list in my calculator, so like we did before, where we put the sum into the y equals and then found this list of partial sums, I can see that this output is going to approach 3 as we continue. And so it does not matter that some of my values were actually greater than 3. It just matters what my limit is as n gets larger and larger. And so in example 6, we want to find the first 10 partial sums for the series of, and this is a 0.5 to the power of n minus 1. And so you can look at this as 0.5 to the power of n minus 1, which is the same as 1/2 to the power of n minus 1, whatever you prefer. And so in part A, I'm going to find the first 10 partial sums of the series. Let's use a calculator. That would be very tedious. I don't want to do this kind of thing without the calculator. And so pulling up my calculator, I'm going to start by just putting this summation into my y equals, so going to math, down to sum, which is item 0. And so going down, yep, item 0. And my n is starting at 1. It's just going to get input as an x. Totally okay. That's starting at 1 and it's going to x. I don't want to put an upper bound. Now, if I put the upper bound of 10, then my calculator is just going to give me a list of the 10th partial sum, which isn't what I want, and that's why I want to leave this upper bound as a variable. And inside of the summation, I have my 0.5 to the power of x minus 1. If you have an older calculator and these values don't actually get shown in the exponent, just make sure you put parentheses around these. All right. And so now let's go to the table. And I'm already all the way at 18 now. If I start at a ridiculous value, I can go to second window to just press table start at 0. And if I'm not going up by 1, because remember, n is just the next consecutive integer. And so I'm starting at 1 or 0 in some cases, and then I'm just going up by 1. So my change in these table items, my change in x really should always be 1. And I meant to go to the table. Let's go to the table, and I can see that n has to start at 1 so that we don't get an error. All right. And these are going to be the first 10 items in this 10 partial sums in this series. And let's look at number 10. So number 10 is getting close to 2. Actually, if I keep going, I'm getting close to 2. This might give me a hint that that might be the limit. But let's not get ahead of ourselves here. Let's just first start by copying down the first 10 values. I'm going to make sure I write them in this partial sum notation. All right, so that gives us part A. Part B, we want to graph the sequence and the sum. And we're told that to graph each of the partial sums, use n for the ending n. Well, we actually already kind of did that when we put in that summation for to find all these first 10 partial sums. And so let's go to our calculator and use the methods we learned in the first section. And so I'm going to switch my mode over to parametric. So I'm going over to parametric mode, and I want to switch this from connected to dot. And I can graph the sequence and then the sum. And so let me just start by graphing the sequence. And I'm just going to go by t, so I'm going to allow my x to be equal to t, and my y will be equal to 0.5 to the power of t minus 1. And let me adjust my window a little bit. And so I want to go from 0 to 10. And I want my t-step to be 1. I want my x-min to be 0, and my x-max I'm going to go up to 10. And just remember this is going to be the same because x is equal to t. My x scale is 1, and for my y values, let's go from 0 to 2.5. Okay. And so going back to y equals, and I'm just going to change this curve to dotted. If you have one of those newer calculators, you probably won't be dealing with this sort of thing. And so now we see a better idea of what this looks like. All right. And so this is the graph of the sequence, not the series. I can see that these values are getting smaller and smaller, and let's see if I can make these dots any bigger. All right, this is going to have to do. And so this is our graph of the sequence. And so let's just take a picture of this. And so we can just note that this is the sequence. And now let's find the series. Let's go back to our calculator. And now we're going to change this to that sum. And so let's leave x as t. And let's change y1 as the summation of, and now I'm going to have the same values. I want t to start at 1, and I want it to go to t. And then here, I want to have 0.5 to the power of t minus 1. All right. And now right here, I see the sum. And so let's take a picture of this in the same way to add to our notes. And we can make note that this now is the sum, or the series. And so what this tells me is that, and I know this occurs at 2. This is 2. It's like this is 2. All right. What this tells me is that my individual values are getting smaller and smaller as n increases. I know that if I have 1/2 and I'm raising it to the power of n minus 1, as n gets really large, this denominator is going to get really small. And I know that this sequence converges, but let's find out if the sum converges. So this is part B. And for part C, does the sum converge? Or the series, I'm sorry. Does the series converge? And for this, before I do this algebraically, I'm looking at the sum of the series and I'm saying, is there a limit as x approaches infinity? And I can see, and I saw that on the table too, that these values are approaching 2. And so yes, this series converges. And now for part D, let's actually show this, and I want to show the sum. And I can see that the sum is 2 because the limit is equal to 2. In part D, I'm going to use the idea that this is in the form of the sum of A times r to the power of n minus 1. Now I know my r is 0.5 or 1/2, so my r is 1/2. And because the absolute value of r is less than 1, this is a true statement, I can say that this converges. And because I know that this converges, I've got my r, my a is just 1. And now I know that the sum is just equal to a over 1 minus r, which is just 1 over 1 minus 1/2, and 1 divided by 1/2 is 2. And again, we found that the sum is 2, and we found this kind of algebraically. And so this gives a good idea of our different options here and how we can show that this does in fact converge or diverge. Now let's look at example 7. In example 7, it's not as easy to see if this sum converges or diverges. This goes from n equals 1 to infinity. But now I have 2 to the power of 2n times 3 to the power of 1 minus n. And so my goal is to rewrite this as the sum from n equals 1 to infinity of a r to the power of n minus 1. So I want to just rewrite this, not actually change anything. So this is where a lot of this algebra is going to come into play. Well, I have the sum of 2 to the power of 2n times 3 to the power of 1 minus n. Let's start by kind of splitting up some of these components. Well, 2 to the power of 2n, isn't this the same as 2 squared to the power of n? To the power of n. Because I know when I raise a power to a power, I'm just multiplying, right? And so this can be called 4n, 4 to the power of n. Now this 3 to the power of 1 minus n, I can say I'm multiplying this by 3 to the power of 1 times 3 to the power of negative n. All right. Now I want this n to be positive. So how can I get this exponent to be positive? Well, maybe I can throw it in the denominator. I know that I can flip the sign of these exponents if I throw them in the denominator. And so maybe I can write this as 4 to the power of n divided by 3 to the power of negative 1 plus n, or 3 to the power of n minus 1. You okay with that? We're just flipping the signs of both of these exponents. And again, I didn't really change anything. Now I have a power of n minus 1 in the denominator, and how do I get this power of n minus 1 in the numerator? And I'm remembering that algebraically I have to do the same thing to the numerator and the denominator. And so if I multiply this by 4 to the power of negative 1 over 4 to the power of negative 1, this will give me 4 to the power of n minus 1 over 3 to the power of n minus 1 times. Now this to the power of negative 1 got put in the numerator, but I don't want to include this 4 to the power of negative 1 in the denominator. And what's a denominator of 4 to the power of negative 1? Well, that's a numerator of 4 to the power of positive 1. And so finally I can write this as 4. Now that I have the same exponent in the numerator and the denominator, I can write this as 4/3 to the power of n minus 1. And now I know that a is going to be 4. Now that I got it in this form, and my r is going to be 4/3. And because the absolute value of 4/3 is greater than 1, the absolute value of 4/3 is greater than 1, this diverges. This is divergent. And there is one other way that I can do this. If I can't quite figure out the algebra, there is an alternate method. And that is just to write the first few terms of the series. First few terms of the series. And so let me start with n equals 1. So with n equals 1, when I plug in a 1, I get 2 to the power of 2 times 1. So 2 to the power of 2 times 3 to the power of 1 minus 1, 3 to the power of 0, and so this is going to be 4. So my first term of this series is 4 when n is equal to 2, or I can also call this A1, A2, however I want to call that, A1, A2. I'm plugging in a 2, I get 2 to the power of 4 times 3 to the power of negative 1. Well, 3 to the power of negative 1 is 1/3, and so this is going to be 16 times 1/3 which is 16/3. So A2 is 16/3. Let's do one more. A3 for n equals 3. When I plug in a 3, I get 2 to the power of 6. 2 to the power of 6 is 64. I'm multiplying this by 3 to the power of -2. And I get 64 times 1 over 3 squared, which is 9. And so this is going to be 64 ninths. So plus 64 ninths. And so I've written out the first few terms in the series. This is enough to show me that I have an A of 4. So my starting value is 4. And I can solve for my R. I can see what I have to multiply 4 by to get 16/3. And so 4 times R is equal to 16/3. Dividing both sides by 4, I get that R is 16/12. Dividing the numerator and denominator by 4, I get that R is 4/3. Same thing I found above by rearranging this. Either way, because R, the absolute value of 4/3, is greater than 1, I get the same conclusion, that this is divergent. So just another way you can go about this. And so that's it for the geometric series. So now we're talking about another example of an infinite series called the harmonic series. The harmonic series. The harmonic series is the sum of values from n equals 1 to infinity of 1 over n. And in this case, our numerator has to be a constant, and the denominator has to just be n. It can't be n to some power, it's just n in the denominator. This harmonic series is always going to be divergent. And here's why. All I'm saying with all of these values is we found the sums for n equals 2, 4, 8, and 16. And due to some algebraic tricks to make this summation a little bit easier, essentially what we found is that our summation is increasing as n is larger. And if this sum continues to get larger as n equals larger and there's essentially no cap, then this harmonic series is going to be divergent. And if we remember back to section 7.8, so remember from 7.8, we found that the integral from 1 to infinity of 1 over x dx was divergent. So this diverged as well. And so although the denominator is getting larger and larger, meaning my fraction's getting smaller and smaller, it essentially isn't decreasing at a rate enough to give us any set cap on these values. And we kind of proved that when we talked about this being either a finite or an infinite area under the curve. In the case of 1 over x, which, and let me just draw this in the first quadrant because x is going from 1 to infinity, we said that although this curve was asymptotic and got closer and closer to the x-axis, this curve didn't dip down soon enough or quick enough for us to have a finite area. So we kind of see the same idea here with the series. So let's just keep that in the bank. Harmonic series is always divergent, All right. Just one more thing to note here, The following series are both still harmonic because I can take, much like an integral, I can take any coefficient out to the front of this summation. So I can call this 1 over 2n. I can say that this is the same as 1/2 times the sum of the harmonic series 1 over n. Likewise, 3 over n, I can say this is the same as 3 times the sum of 1 over n. So any kind of constant in the numerator and a coefficient in the denominator doesn't affect the fact that this is a harmonic series. It's just that this n can't be raised to any kind of power, and there can't be a variable in the numerator. All right, and with that, we have one more theorem. And that's that if the series of the summation from n equals 1 to infinity of an is convergent, then the limit as n approaches infinity of an is equal to 0. And so if we think about it, it makes sense, because I remember that a sub n represents just these values in this series. So this series is going to be the sum of these a sub n values. So this is going to look like a1 plus a2 plus a3 and so forth onto infinity, because this is an infinite series. Now, in order for this summation, so in order for all of these values added up together to be some finite value, these individual values of the sequence that this would form must be getting closer and closer to 0. And so the limit of a sub n must be equal to 0, because if it's not 0 and I continue to add any positive, negative, or otherwise non-zero value infinitely, then I can never find a finite sum because I'm adding anything other than 0. It might seem a little bit obvious. And so this is where this theorem comes from. It's really called the test for divergence. It states that if the limit of a sub n as n approaches infinity does not exist or otherwise does not equal to 0, then the series as a whole must be divergent. So if the individual values do not go to 0, then the series must be divergent. Now this doesn't necessarily work the other way around. And so just be careful, because the converse just means this flipped is not true. And let's think of the harmonic series in general. So the harmonic series is the summation of 1 over n. We know this diverges. But if we were to show that it diverges by showing that the limit of 1 over n as n approaches infinity, we know that this is going to be 0, right? As my denominator approaches infinity, this is going to give me a limit of 0, but just because the limit of a sub n is equal to 0 doesn't necessarily mean that this converges. It just means that if the limit's not equal to 0, I can automatically determine that this diverges. And so this is our test for divergence. This, in my opinion, is probably the easiest way that we can prove divergence. And so this is one of those things where, and we'll talk about this more as we go along and find more tests, I would go for the test for divergence first, because it's very easy to determine whether this a sub n has a limit of 0 or not. Now, if this test fails, this can either converge or diverge. Again, if the test for divergence fails, it doesn't really say anything about the convergence, but it just proves that if this test succeeds, then the limit's not equal to 0, then this series automatically diverges. All right, and so let's do an example of this. Example 9. We want to show that the series diverges, and let's use the test for divergence. And using the test for divergence. Now, this is not in the form, let's just make a note here. It would be difficult to get this in the form of the sum of a r to the power of 1 minus n. ar to the power of 1 minus n, remembering that this is our geometric series, or I know this is not in the form of 1 over n, which is our harmonic series. Right now, these are the only types of series that we know how to make conclusions about. So this is why I'm going to use the test for divergence, and I'm just looking at this a sub n. In this case, my a sub n is n squared over 5n squared plus 4. And so let's find this limit. And so this is going to be the limit as n approaches infinity of n squared over 5n squared plus 4. Well, I know that if I have the same degree in the numerator and the denominator, my limit is just this fraction of the leading coefficients. And so my limit is just going to be 1/5. And because 1/5 is not equal to 0, I can just say that this series diverges. And so since, and I'll put this, since the limit as n approaches infinity of a sub n is not equal to 0, the series is divergent. I've proved that it diverges. No more work is necessary. And so that is the simple beauty of the test for divergence. Let's talk about one more idea. And hopefully you can see it, hopefully it's clearer on your notes, but it's this idea that if the sum of a sub n and the sum of b sub n are convergent series, then so are the series of the sum of c times a sub n, where c is a constant. So are the sum of the series of a sub n and b sub n and the difference of that sum. And so this is essentially what we're saying we can do, that we can split these up into different sums. If we want to find the sum of a series, and it's actually a sum of different values, of different expressions, then we can break up these summations. So let's see what this is going to look like with real values. In example 10, we want to find the sum of the series of 3 over 3 to the power of n plus 1 over 2 to the power of n. And let's remember that I want this to be in the form. Now I know this is not a harmonic series, right? And so I want this to be in the form of a geometric series. I know this isn't a harmonic series because I can't get this 3 to the power of n or this 2 to the power of n to be just an n. And so this must be a geometric series, which I want in the form of sum a times r to the power of n minus 1. So this is my goal. And I can split these up. That's what this theorem is saying, that I can split these up, and I can split this up into the sum of 3 over 3 to the power of n and the sum of 1 over 2 to the power of n. And I'm not going to write this n equals 1 to infinity because that's my assumption. If I don't have this here, then I can assume I'm going from 1 to infinity. So and you can write it out. You just don't need to write it out every single time. And so how do I get this power to be n minus 1? Well, I know that when I have like basis, I can add these exponents by multiplying. And so what if I were to multiply this? If I want this denominator to have an exponent of n minus 1, then I need to multiply this denominator by the same base with an exponent of negative 1. And if I'm multiplying the denominator by the same base with an exponent of negative 1, I need to do the same thing with the numerator. And so doing so, I get 3 times 3 to the power of negative 1. Well, 3 to the power of negative 1 is 1/3. And so 3 times 3 to the power of -1 is 3 times 1/3, which is just 1. And so I'm left with the sum. I've got a numerator of 1 divided by 3 to the power of n minus 1. And I know 1 to any power is just 1. And so that means that I can break this up into 1/3 to the power of n minus 1. And so now my a is just 1. This is now in the form of a times r to the power of n minus 1. So my a is just 1, and my r is equal to 1/3. Just ensuring that this summation is convergent, that this left part of the series is convergent, I know this 1/3 is less than 1. The absolute value of 1/3 is less than 1. Great, just checking to see if this converges. And on the right, I'm going to follow kind of the same process. If I want this exponent to be an n minus 1, I'm going to multiply this denominator by the same base with an exponent of -1. And I need to do the same thing to the numerator. But now 2 to the power of -1 is 1/2. And so now I have the sum, and I've got a numerator of 1/2, and my denominator is 2 to the power of n minus 1. And remember, I can pull out, just like I would an integral, I can pull a coefficient out to the front of this summation. So I can pull this 1/2 out to the front of this summation. And I can write this as 1/2 times the sum of 1 over 2 to the power of n minus 1. I really didn't need that parenthesis there. Okay? And so now I can rewrite this as 1/2 times the sum of 1/2 to the power of n minus 1. Great, now this is in the form of that geometric series, and now I can see that my a is equal to 1/2, and my r is also equal to 1/2. And so now I need to find two sums. Let's kind of color code these. I want to find the sum of the first part of this and the sum of the second part of this. And so for the first portion of this, I'm finding this first sum. For the second portion of this, so for the second summation, I'm finding the second sum. And I know that because I'm adding these two together to find the total, I'm just adding these final values together, these final summations. And I know that my formula for the sum in general is equal to a over 1 minus r. And this is going to give me, first I've got an a of 1. My denominator, I've got 1 minus r. My r is 1/3. Well, 1 minus 1/3 is 2/3, and 1 divided by 2/3 is 3/2. And so this is the sum of this first portion. For the second portion, I've got an a of 1/2, and I'm dividing by 1 minus r, which is also 1/2. This is going to be 1/2 divided by 1 minus 1/2, which is 1/2, and so this is just going to be 1. And my total sum of everything is going to be 3/2 plus 1. 3/2 plus 1, which is equal to 5/2. So if I add everything together, I get a total sum of 5/2. And finally, I can check this in the calculator. Let's quickly check this in our calculator. If we graph the summation, so let's go back to our function mode. and I've got this summation of, let me put everything in here. So 3 divided by 3 to the power of n. So 3 divided by 3 to the power of my variable. And I'm adding to that the quantity 1 divided by 2 to the power of my variable. And let's see, let's go to the table for this. And in my table, well, and normally I would start at a lower x value, I can see that as x increases, my y values get closer and closer to 2.5, which is 5/2. Great, and so we found the correct sum. And so that is it for series.